Scientists were supposed to be finished with 3i Atlas by now. The interstellar visitor came in, lit up our feeds, broke a few models, split the community into weird comet and possible probe camps, and then began the long, slow slide back into the dark. On paper, that should have been the end of it. You do the press conferences, you publish the big papers, you write the What We Learned blog posts, and you move on to the next object. Except that's not what happened. Before we continue, if this has your attention, you can subscribe, turn on notifications, and hit like anytime. And for the best viewing, switch to full screen and enjoy what's coming next. Because if you look at what astronomers are actually doing this week, the real observing schedules, the telescope requests, the late-night coordination email, Atlas is still there, not as a footnote, as a target. Telescopes that could be pointed anywhere are still tracking a fading speck that's already leaving the inner solar system. Teams that should be on to the next project are still squeezing time out of their nights to stare at something that, for most people, is old news. So the obvious question is, why? Why are scientists still watching 3i Atlas this week? What are they afraid of missing? If you've been following this saga with me and you don't want to miss whatever happens, if this object decides to misbehave one more time, make sure you're subscribed, drop a like, and stay with me until the end. Because once we walk through what they're actually measuring right now, you'll see that the most important part of 3i Atlas's story might not be what it already did, but what it hasn't done yet. Let's start with the simple story everyone expected. A comet, even a weird one, follows a familiar arc. It enters the inner solar system from the cold, quiet, dark. It warms up. Says sublimate. Gas jets erupt. Dust lifts off and spreads into a coma and tail. The object brightens as it approaches the sun. That's the part everybody photographs for wallpapers. Then it passes perihelion, the closest point to the sun, and starts heading back out. The sunlight weakens. The energy drops. The jets shut down. The coma collapses. The brightness fades along a smooth curve that you can write down in a single equation. After that, the science becomes routine. You take a few more measurements to confirm the fade matches your model, and then the object is simply too faint to justify time on big telescopes. The story ends with a graph, not a cliffhanger. That's what should be happening with 3i Atlas right now. But it isn't. Instead of sliding quietly down the curve, its brightness is arguing with the script. When astronomers plot the latest photometric data, how bright 3i Atlas is in different filters over time and lay it over the normal fading law for a comet at its distance, the points refuse to behave. They're not screaming. There's no giant last-minute flare. That would be simple. What the real measurements do is much more annoying. They sit slightly above the model, night after night, telescope after telescope. Different observatories, different instruments, same pattern. 3. Atlas is not fading as fast as it should. At this stage, the coma ought to be collapsing into a tired, diffuse glow dominated by old dust coasting away. Instead, the inner region still has a sharp core. When you stack the images, tiny bumps appear in the light curve. Small, but real. And this week is critical, because we're right in the window where the curve has to choose a side. Either it finally bends down toward the expected decline, or it keeps stalling and proves that the current phase of activity isn't done yet. That's reason number 1. Scientists are still watching 3i Atlas this week. They're trying to catch it in the act of deciding what kind of object it really wants to be. A standard flare and fade comet. Or something that keeps drawing energy from deeper layers longer than our models expect. To answer that, you can't just glance at it once and walk away. You need dense sampling, you need multiple nights. You need to see if those small bumps repeat, if the inner coma maintains its structure, if the brightness is tied to anything else. And that leads directly to the second reason they can't look away yet, the spin. From very early on, people noticed that 3i Atlas didn't just shine. Its brightness rose and fell in a pattern that looked less like a smooth rotation and more like a heartbeat, depending on how imaginative you're feeling. An engine note, content reference, OA site, index 5, closing parenthesis. Comets vary in brightness. All the time, they spin, they tumble, they vent more on one side than another. That's normal. But 3i Atlas's light curve was different. In the raw data, you saw a dominant peak with smaller pulses riding on top, and those pulses had a rhythm not perfect, not machine-like, but persistent enough that some researchers started using words like pulsed jets instead of uneven surface. If the nucleus were just a small, elongated chunk of ice and rock tumbling, end over end, you'd expect a certain kind of regularity. A single, clean period, a bright side and a dark side, flipping in and out of view. Instead, what scientists saw looked more like multiple active regions taking turns. One side vents strongly. The brightness spikes. As it rotates away, a second hotspot swings into sunlight and fires. Then a third. The result is a light curve, with multiple peaks per rotation, each peak corresponding to a patch of the surface, behaving like a miniature engine. That alone would be worth watching. But then, the period itself began to drift. If you take several nights of data and fold them over a single assumed rotation period, the peaks should line up. But when astronomers tried that with 3i Atlas, the peaks kept arriving a little earlier than expected, then earlier again. The best fit period had to be shortened. Over time, that drift told a clear story. The comet was spinning. Jets weren't just venting. They were applying torque, like a tiny, uneven thruster, firing off tear. They were gradually changing the spin state of the nucleus. That's dangerous territory for a fragile object. The faster you spin, the more centrifugal force you feel. For a fractured, porous body, made of ESAs and dust, there's a limit. Go past it, and you risk structural failure, fissures, shedding, fragmentation. So what do you do if you're a scientist who wants to know whether 3i Atlas is on the path to stabilizing or self-destruction? You've watched the light curve. Again, that sounds simple. In practice, it means eating entire nights. You have to track the object for hours at a time, taking exposures over and over, then repeat that on multiple nights. You have to coordinate between observatories in different time zones to fill gaps. You have to fight weather, instrument quirks, and the fact that this thing is getting fainter by the day. And you have to do it now this week because every day you wait, the object gets harder to measure. The goal is to answer a very specific question. Has the spin finally stabilized? If you fold this week's light curves over last week's best period, do the peaks land cleanly? Does the secondary structure keep the same shape? Or do you have to tweak the period again, shave another fraction of a second off, bend the curve a little more? If the period holds, that suggests the torque has eased. The jets might be relaxing. The internal stress could be leveling off. If the period continues to drift, even slightly, then the forces twisting this nucleus are still at work. The stress is still evolving, and collapse or fragmentation stays on the table. That's not something you can reconstruct later from memory. If 3i Atlas does come apart farther out, people will turn back to this week's data and ask, did the light curve warn us? If the answer is yes, it will rewrite how we treat stressed comets in the future. If the answer is no, that's even more disturbing. Now, brightness and rotation are only half the story. The other half is written in dust. Out of everything we've learned about 3i Atlas, the dust has been one of the hardest things to explain away as just another comet. Think about how a normal comet's dust behaves. You have a range of grain sizes, from tiny smoke-like particles up to larger chunks. The smallest grains get pushed away by sunlight radiation, pressure, and form the long, classic tail you see in pictures. Heavier grains tend to hang closer to the orbit, forming a trail. 3i Atlas didn't play by those rules. When it developed a striking feature pointing roughly back toward the aeon and enetitle, most astronomers reached for the standard explanation, geometry. Sometimes, when Earth crosses the orbital plane of a comet, the dust trail behind the comet lines up with our line of sight and looks like it's pointing the wrong way. Optical illusion, perspective, nothing to see here, except this. Time. The physics said otherwise. Content reference, OA site, Index 6. When people like Avi started modeling the dust, they discovered that the grains in that structure weren't tiny fluffy specks. They were big by interstellar dust, standards around 10 microns across, 10 times larger than typical grains drifting in the galaxy. That size matters. Grains that big are heavy enough to resist being blown away by sunlight. They can swim upstream against radiation pressure and assemble into a sunward pointing jet or sheet. But they're also heavy enough that the gas flow from the nucleus has sought to work hard to lift them off the surface in the first place. You need a very specific range of sizes to make the whole thing work. Small enough to be entrained, large enough to resist being stripped away. When you crunch the numbers for 3i Atlas, you land right in that narrow sweet spot. Then it gets weirder. Estimate how many of those grains are packed into the dust veil, and you find that the cloud's optical depth eats thickness in terms of how much light it blocks is close to 1. Content reference, OA site, Index 7. That's a critical threshold. An optical depth of 1 means the cloud is just thick enough to obscure direct views of whatever sits behind it, but not so thick that it becomes a black wall. It scatters light efficiently. It hides detail without going fully dark. You can, if you choose, interpret that as an extraordinary natural coincidence. A tiny nucleus, wildly active for its size, somehow producing a veil of dust with exactly the properties you'd dream up if you wanted to shield something from the sun and prying eyes. Or you can ask the more uncomfortable question, is this veil behaving like a designed shield? Now, whether you land on natural or engineered, the immediate observational consequences are the same. You have a structured dust environment around 3I Atlas that is going to evolve as it recedes. Those grain streams are going to stretch out along its orbit. They're going to get twisted by solar gravity, radiation pressure, and solar wind. Even after the nucleus is too faint to see, those dust structures will remain part of the solar system. And this week, scientists are still stacking deep exposures to watch that architecture ripple outward. They're asking, is the anti-tail still feasible? If so, has its length or brightness profile changed? Does the inner veil around the nucleus look thinner, thicker, more asymmetric? Can we trace the emerging dust trail that Earth and other planets will eventually cross? Every one of those questions matters for the long-term impact of this one flyby. If you want to predict future meteor activity from 3I Atlas, you need a good handle on where it left its debris. If you want to understand how interstellar dust streams integrate into our own zodiacal dust cloud, these late-time images are your only chance. Nobody gets to re-observe this phase later. On the other side of the data pipeline, dynamicists are doing something just as obsessive, arguing with gravity. In all the orbital calculators, 3I Atlas is supposed to be an almost perfect test case. For Newtonian mechanics, an interstellar object comes in on a hyperbolic trajectory, gets its path gently bent by the sun and the planets, then sails out, following a curve you can write down precisely. But that's not what the real orbit looks like. From very early on, people had to add a non-gravitational term to make the ephemeris match the observations. The object was being pushed by its own jets, outgassing, acting like tiny thrusters. Its path was self-steering enough that NASA began warning about growing uncertainties. Content reference. Site index 8. It passed Earth safely, far away. There was never a threat, but the fact that its trajectory kept needing updates, tweaks, and new fits was a sign that the interior engine would ever. You think that engine was not a one-time burst? It kept firing. So when you hear scientists are still watching 3I Atlas this week, part of what's going on is this. Astrometric teams are still measuring its exact position in the sky, down to fractions of an arcsecond, then feeding those coordinates into orbit solvers to see how much extra push they still need. If the latest astrometry can be fit with a smaller non-gravitational parameter than last week, that suggests the jets are finally calming. If the best fit solution wants the same, or even a larger term, that means the comet is still actively pushing on itself in ways that matter for its trajectory. And just like with brightness and spin, this week is in a transitional zone too early, and you can't tell if the changes are just noise. Too late, and it's too faint to get good positions. Right now, the measurements you take can decide whether the outbound path of 3I Atlas will be remembered as smoothly decreasing thrusts or continuing to thrust longer than expected. That distinction matters a lot more than you might think. If this object really did maintain active self-steering far into the outbound leg, that's yet another piece of evidence that it doesn't fit neatly into standard comet categories. In a natural scenario, it suggests a macroscopic structure that can sustain activity deep into its interior, not just at the surface, possibly a fractured, layered, or even hollowed-out geometry. In a technological scenario, it suggests a propulsion system capable of operating for long stretches without obvious refueling, using volatiles like CO or CO as per content reference. Bashi sheet, index 9. Either way, it pushes us toward new models. Then, there's the part that almost nobody hears about unless they go digging through dull-looking reports, the silence. Throughout this encounter, arrays like Green Bank and other radio observatories have pointed their dishes at 3I Atlas, listening for narrowband radio signals, the kind you really only expect from technology, content reference, eyes sight in. So far, they've heard nothing. On the surface, that supports the just a rock camp. If it were aliens, surely they'd say hello, right? Not necessarily. If 3I Atlas were a derelict probe, it might be dead, drifting with no power and no transmissions. If it were an autonomous surveillance asset, it might be designed explicitly not to talk loudly in radio near other civilizations. You don't spy on a house by installing a giant loudspeaker in the front yard. Or, more mundanely, it might simply be using communication methods we're not listening for. Or, transmitting in short bursts outside our observational windows. Either way, radio silence doesn't close the case. What it does do is create a moving upper limit. Every additional hour of listening this week tightens the constraints. It lets scientists say, if there is a transmitter on or near this object, it is below this power level, at these frequencies. With this duty cycle, that's why, even as the optical brightness drops, some teams are still sneaking in observations at radio and other wavelengths. They know that whatever 3i Atlas is, it's one of only 3 confirmed interstellar visitors we've ever seen up close. Weak limits are still limits. Null results are still data. And if, by some strange twist, a new signal did appear, by a change in environment, a structural failure, or a final burst transmit event, you'd only catch it if you were still listening. So we have brightness that won't behave, rotation that won't settle, dust that looks engineered, an orbit that needs extra push, and radio ears still pointed at a fading dot. That would already be enough to justify why scientists are still watching 3i Atlas this week. But there's one more layer to this, and it has nothing to do with this object on its own. It has to do with the pattern. We like to name things, one by one. 1i Oumuamua, 2i Borisov, 3i Atlas, the first visitor, the second visitor, the third visitor. But when you line them up, the comforting idea that interstellar visitors are rare and boring starts to evaporate. Oumuamua was tiny, dark, and disturbingly weird. No clear coma, no classic tail, but a measurable non-gravitational acceleration. As it left, like something was pushing it gently from within, without any obvious gas. People proposed hydrogen ice, nitrogen ice, fractal dust, solar sails. Borisov looked more familiar. Lots of gas, lots of dust. Classic cometary behavior. Chemical ratios that suggested it came from a different kind of stellar nursery than our own. 3i Atlas arrived and combined the worst of both worlds. A small nucleus, acting like a huge one, an overachieving coma and tail. A dust veil that behaves like a shield, and course changes that made agencies reissue their orbit warnings. Content, reference, Site Index 11. 1 weird rock is an anomaly. 2 is interesting. 3 starts to look like the universe is trying to tell you something. There is, in other words, a new branch of astronomy unfolding in real time. Interstellar object science. And 3i Atlas is its current lab rat. This week's data doesn't exist in a vacuum. It flows directly into proposals for how we'll handle 4i, 5i, and 6i. How sensitive do our surveys need to be? How quickly do we need to classify their behavior? What combination of light curves, spectra, and orbit fits tells us this is worth a dedicated mission? If we want to someday send a probe to intercept one of these visitors, the experience with 3i Atlas will define what we think normal looks like and what counts as you need to launch now. That's the real long-term reason why scientists are still watching this week. It's not loyalty to one object, it's training. Every late-time data point on 3i Atlas is a rehearsal for the next interstellar visitor. Observatories are practicing rapid response scheduling on a fading target. Modelers are stress-testing their non-gravitational acceleration codes on a real, misbehaving object. Instrument teams are learning how far they can push their hardware to squeeze signal out of an interstellar speck sinking into background noise. Someday, if we're lucky, another interstellar object will appear with enough warning and a slow enough speed that we can throw a spacecraft at it. When that day comes, the decisions we make, where to aim, what to measure, how to interpret early anomalies, will be shaped by this weird little object we're still tracking now. And that changes the emotional meaning of why are they still watching 3i Atlas this week. They're not just watching the end of a story. They're watching the beginning of a playbook. In the end, the answer to why comes down to this. We don't get many chances like this. You can study local comets whenever you want. There are hundreds. If you miss one, another will be along in a few years. You don't get to say that about interstellar visitors. So far, in all of human history, we've seen 3. One came and went before we knew how to look for it properly. One arrived while we were still building our tools. This one, Atlas, is the first, where we're taking it personally. That's why, even as the world forgets, there are still people in control rooms this week. On mountaintops and in deserty arrays, lining up faint guide stars and telling their software, track that dot again. They're not just afraid of missing a dramatic, last-minute surpriser's sudden flare, a split nucleus, a final goodbye jet. They're afraid of missing the quiet clues, the small deviations, the subtle transitions that tell you whether this is a comet dying, a comet adapting, or a comet that was never quite a comet in the first place. So the next time you see a tiny, dull-looking update new light curve from 3i Atlas, revised non-gravitational parameter, dust morphology as of this week, you'll know what you're actually looking at. Evidence that somewhere out there, people are still refusing to look away. Because until 3i Atlas finally drops below the reach of our instruments, it has one job: to keep telling us what interstellar space is really like. And we have one job: to listen. If you want to keep following that with me through whatever this week's data shows, through the next unexpected bump on the light curve, and through the moment when 3i Atlas finally slips into the noise floor for good, make sure you're subscribed. Drop a like so this reaches more people. And tell me in the comments, If you had one more night on a big telescope with 3i Atlas, what would you measure? Its heartbeat? Its dust veil? Its shrinking? Push against gravity. Whichever you choose. Remember, the visitor may be leaving, but the reason we're still watching it this week is simple.